Hi there, guys. So we're about to do 15E, and this is before we shift on to spanning trees. So there's some algorithms to make spanning trees next. So we're kind of finishing off the first little period of work here. And this is quite nice. We're making transition matrices. So in other words, the probability of going from, say, A to B to C and so on, wherever you are in your network. I'm going to go through the mechanics of this basically. And so if we have a look at this here, I've just started making the matrix to say this is the adjacency matrix, and then I'm going to come up with how to make the transition matrix. So the adjacency matrix is what we've dealt with before. So say, for example, for A, we can see that there we can go on to B, D, and E. So what we're talking about there is A moves on to B, to D, or to, sorry, not E, F in that case. So there's the three possible ways of that happening. But A can't go to, say, C because it's a backwards arrow there. So what I've done over to the side is I've made the adjacency matrix. I've missed out the last line. The last line is just E, and you can see that E goes to F rather. F is the last of the lines here. So F is the line which I've missed out, the row which is missed out here. And you can see that F can go to two places. It can go to A or it can go to E. So I can put a 1, a 0, a 0, a 0, a 1, and a 0 in there. Now, in fact, the way I made that was actually by cheating and looking at the answer to the transition matrix, because the two things are related. So you can see how they're related in terms of this last column here represents this row. So that is the column for F, and it's basically saying, look, here, if we had a choice for F as to where we're going to go, we're going to go, we can either go to A or we can go to E. And if you were walking randomly here, then you would move between the vertices with a half chance of going to A and a half chance of going to E. Now, the whole thing is transposed, which means to say that the columns and the rows are switched around. And that's because you're applying this by multiplying a potential original set of potentially people who are at each of these vertices, and then they're moving to each of the vertices, or potentially there's a set of probabilities that you're at a particular vertex, and then we're going to apply this transition matrix across. So what's going to happen here is that we're going to apply, just re-recording this a little bit here. I was putting the vector on the end of this one. I meant to put the vector on the end of this one. So I'm talking about why the matrix here needs to be a transposed version of this, and where we get the probabilities from. So if we were going to apply a transition matrix to a set of people who are numbers of people who are at each of the vertices, or potentially probabilities of people being at those vertices, so that's what could be in here. So say, for example, we have 20 at the top. That means to say we have 20 of people currently at A, and what's going to happen to them. Now, when we apply this first line, say, for example, this applied to this, that's going to give us the answer. So we're going to do 0 times the first, and 0 times the second, and then a half times the third one. So what that's saying is that if you're currently in C, to go from C, you can't go back to C, but you can now go to A or B. Now, you can go to either of those with a half chance each, because there's two choices there. So you're going to get a half of your options from C are going to end up in A. And then, of course, you're going to do 0 times by D and 0 times by E, and a half times by F. So what was in F previously, goes with a half chance to A and a half chance to E. So the half chance to A is being counted here. And that's because we've got essentially a 1 there and a 1 there, and the probabilities are coming from the rows essentially. Okay, and so that's getting transposed in this case because we're doing matrix multiplication where we're doing our rows times by our columns. Okay, so what we'll end up with by timesing this by this is an answer with what we expect to end up then in A afterwards. So in other words, half of whatever was in C is going to end up in A, and half of whatever was in F is going to end up in A. Okay, so that's why we're transposing these things. We're transposing from the adjacency matrix. And again, the probabilities are actually really easy to get here because we're talking about saying, well, look, for A goes on to B, D, or F with an equal chance in a random walk. So that's going to be a third chance for each of them. So your column is going to be filled with thirds there. And then, for B, we've only got one choice. So all of the probability goes then from B to D. You have to go from B to D there. Okay, so this is a transition matrix, and we can apply it as many times as we want. So construct the transition matrix, pretty easy to do. We need to come up with probabilities from our rows, and then we need to transpose that matrix from the adjacency matrix. Okay, so we've constructed the transition matrix. There it is. This is the thing here. And then it says, find the steady state probabilities of the network. So for this one, you could essentially say, well, I'm going to make this vector here of, say, I don't know, I'm going to put in equal probabilities of a sixth in all of these to say that a sixth of everyone starts in each of these places, and then apply this n times. But essentially, it's the same as doing this matrix to the power of a very high number. So let's do that then. So, and basically we need to do that until we've got a steady state matrix, and that will show us our probabilities in our rows, and it will be the same in every row. So let's just try and do that. So let's create this one and create the matrix. We're going to do 6 by 6. Okay, so 6 and tab across here again to 6. Press OK on this one, and I've got a 0, a 0, 0.5, 0, 0, 0.5. So next line, we've got in a third. So I'm just going to put in 1/3 there, 0, 0.5, 0.5, and a third again. So we're going to do 1 divided by 3, a 0, a 0, and I'm going to do 0, 0, 0, and a third again. So 1 divided by 3. So sorry, it's taking a while, but we'll be doing it at the same time. And so the next one is going to be 1 divided by 3. We get 1, 0, 0, 1, 0. And then in the penultimate line, we've got all zeros apart from the last half, so 0.5 there. And then finally, we've got 1 divided by 3, 0, 0, 1 divided by 3, and then 0, 0. Okay, now I'm going to call that something. I'm going to say control and store, so control and variable. I'm going to call it matrix A. Okay, now if I wanted my probabilities of ending up in places in the long term, I need to take that to a high power. So I'm going to do a to the power of, let's try a to the power of 10. And I can see that each of my columns is similar when I do to the power of 10. It's coming up with a long set of numbers there, but you can see that we're getting similar numbers. So like I'm getting 13% in the first top left number, and then 12.75% in the second one. So we're getting similar numbers, but we want them to be the same, basically. So I'm going to do now a to the power of 50. And now I've done that. It's taking slightly longer to calculate, microsecond longer to calculate there. And I can see there I'm getting, to 3 significant figures. I'm getting the same answer in all of those cases. Okay, so I'm getting basically the same vector repeated, column vector repeated throughout that matrix. So I'm getting this thing here. So that's telling us that in the long term, we're going to end up at A with a 13% probability, B with a 20.7% probability, and so on. So obviously you could say, well, what's the probability of ending up somewhere after applying a random walk 10 times? That would be A to the power of 10. But if we want our steady state probability, then we can apply that A to the power of 100, 200, until we get to the same answers in each of the columns. That's going to give us our probabilities of ending up in each of those positions. Okay, and now, like I said, you could apply this to probabilities here at the start, or you could apply it to actual numbers of people who are in A, B, C, D, and so on. So it might be that you have, I don't know, 30 people there to start off with and 20 people in B. And then you could apply this matrix multiple times over to see where you'd end up if they're all taking a random walk of length 2 or length 3 or length 5 or whatever. Okay, then it says, hence rank the vertices in order of importance. So the ranking is essentially then saying, well, look, D is more important than anything else here because you're going to end up there more times than ending up in, say, for example, E. We're going to end up in E fewer times. Now we can see that D is kind of in the center of things. We've got a lot of things going through D, a lot of traffic going through D. It's not stuck out on a limb either side. And, you know, you can see E is particularly stuck out on a limb that hasn't even got an extra branch like C does connecting it. So you can see that E has a poor probability of going through or ending up at. And so we can rank things according to their probabilities here as to the importance of each of the vertices in this network. You can think of this like social networking as well. Okay. This, by the way, is pretty this, I think they tell us in the book here. Let me have a little look. So I think they say that this was used by Google to start off with in order to figure out an importance of different pages and different search results by thinking about the number of links that were going between each of the sites. So one massive transition matrix was created, and then they applied that to a certain high power. Yeah, interesting. It's interesting. This has real applications. Okay, so that's 15E. That's 15E done there. Okay, I'm just seeing if I can see where they were talking about that. No, okay. See chapter 9 and the introduction to Markov chains. It relates to the Markov chains, which we did there as well. Here we go. This is what it said here. It said the Google PageRank algorithm was developed by Larry Page and Sergey Brin in 1996 while working at Stanford University. They wanted to be able to rank the web pages in an internet search so the ones most likely to be useful come towards the top. So basically, they did this, but they did this on a big scale. There you go. Okay, well, thanks for listening in. There's 15E to have a go at next. And then beyond that, we're talking about making minimum spanning trees. And we'll talk about 2 algorithms for that as well.